happy to have you in this program. And it's a privilege for us to have you here. We know Ma'am Meera for a long time now. And I think it has been a wonderful sharing with her. And I'm sure that the participants who are here will get a lot of insights into the ideas of physics education research and how they can be implemented. Because this talk is particularly focused on higher education segment, I think that will add a lot of insight for us to experiment in our classrooms and make use of the researches being done in physics education research itself. Ma'am, I hope you will keep on coming again and extend this idea of physics education research around the country through our members. Thank you very much, ma'am.
Thank you, sir.
Thank you, sir. So I would be delighted to extend an invitation to Professor Sastry. Professor Sastry is a professor from the Department of Physics and Astronomical Sciences at Central University of Himachal Pradesh. And I will invite him to preside over the upcoming session. Professor Sastry, please.
Thank you. Thank you so much, Dr. Sapna. It's indeed a pleasure to be, having this privilege to be chairing this session in which one of my very close friends and an inspiration, Dr. B.N. Meera, is going to share her views on such an important topic, that is physics education research. So, of course, we all know Dr. B.N. Meera from Indian Association of Physics Teachers. She had been the academic secretary for the National Convention of IAPT in 2008 when it was held in Bangalore. And we both happened to, at that time share a lot of, expertise, a lot of time looking through the various papers. So to give a very formal introduction to Dr. Meera, she has completed her master's in physics from Karnataka University, Harvard, and then went on to do her doctoral work, PhD from Indian Institute of Science, a premier institution in the country as well as the world. And she worked on amorphous materials using high resolution NMR and Raman spectroscopy for her doctoral dissertation. After that, she joined as a postdoctoral fellow at BARC, Baba Atomic Research Center, and later on worked also at Homi Baba Center for Science Education. And she's also, of course, being a very gifted researcher, got the fellowship of Fulbright Fellowship, as well as also called as Kilambi Ramavataram Fellowship, which was actually being promoted by IAPT. And she was chosen for this fellowship in 2006-2007. And she had been a visiting fellow, visiting faculty at Kansas State University for 2 semesters during that period. So, of course, her research interests are both in physics education research as well as nonlinear dynamics. And her physics education research group, I think, is the very first in our country. And hats off to you, madam, for embarking on this very, very different field of research. Not at all easy. Even today, we are struggling to make a mark of, in physics education research, because Department of Physics says it is not ours, and Department of Education says it is too high for us. So we are actually always struggling. And so it is really hats off to you that, you had taken the first steps to begin this important research in our country. And of course, she has many papers to her credit in international journals. And she's currently serving as a professor in the Department of Physics of Bangalore University. And she has been associated with the department from 1998. That is close to 25 years now. So very long and very, very distinguished career. We are so happy, madam, to meet you almost after 15 years. I really look forward to your talk and hope that we continue to keep sharing our knowledge with each other. So with this small introduction, I request Dr. B.N. Meera to start today's proceedings, her talk for today.
Thank you, Dr. Shastri, for your kind words. And
you, ma'am.
I must really thank Professor Ahluwalia and Sapna, who are known to me for many years, in at least making people hear about this physics education research. I think some 20 years back when I started, we were just a few handful of us. We were sort of informally looking at how physics need to be learned. Professor A.W. Joshi was one such pregnant personality. I remember he used to say that physics education research has become more of a hobby. Move it from being hobby to a career option. So, I mean,
Very tough.
I tried doing it in this 25 years. It's been very satisfying journey. It had its ups and downs, like Dr. Shastri said, mostly downs initially because physics people thought, what is somebody wanting to do education? Physics people always feel they're really the privileged people, and they thought that what would an education related research do in a physics department? And like Professor Shastri said, education people, if you go and say physics, they say get out. It's not easy. So it was very hard, but fortunately I had a department which has been very open about new things. They said, if you are willing to risk your career, who are we to stop you? That's exactly what they told me. And I've never felt that I risked it. It's been a very satisfying journey. I've tried to do whatever little bit I could do in the area of research. And people like Professor Ahluwalia, who have been so passionate about teaching and physics education research, have been a role model for all of us. So thank you, Professor Ahluwalia. I think my first PER talk was in Shimla University, if I remember. I had just come back from US after my 1-year stint, and I went and spoke to people then. It's changed a lot over the years. Unfortunately, it hasn't changed much in the Indian context, but I'm so glad that IAPT is putting a very, very positive foot forward to at least now give this field of research its due attention. So I would like to start right away going to the talk. So let me just, please tell me if you can see the screen.
Yes, ma'am. Yes, we can.
Okay, yeah. So I start today's talk titled Implications of Pedagogy and its Relevance in Advanced Physics Learning. Like Professor Ahluwalia said, I will be focusing mostly in higher education. As we go along, you will see what is the need for it. And I will try and finish whatever I want to say. I have been a little over ambitious in planning the talk. If I run out of time, I can stop anywhere. It's only to give a flavor of what is done in this area of research. And I assume all of us are physicists and mostly teachers. Therefore, I have sort of arranged the talk to be of relevance to physics teachers. So you will find a lot of physics content in this. So we can go ahead. And I think the way we had done in the last was to take the questions in the end. So please, I have a request, mute yourself. Thank you. So whenever it comes to any of the physics learning, it happens mostly in a formal education context. We are talking of that kind. So the first thing that most of us want to understand is the meaning of what is education. Because this also encompasses what is expected of a learner, I would like to say a few words about it. There are several definitions of education, as many as the factorial number of alphabets in the word education. But the one that I think is relevant for domain-specific expertise is education is the transmission of knowledge, skills, and character traits. That's one thing which is which comes out as one which is relevant for our kind of approach. What is important is people and also teachers and researchers stress the role of critical thinking to distinguish education from indoctrination. I think this is one thing all teachers agree on. We are really not looking at indoctrination is basically to transform information or to transform knowledge. You're also working towards making critical thinking as one of the important component of learning. And you all know as teachers, it's a very tall order. It doesn't happen so frequently. Most often not regularly also. So when you look at education, you can look at, this is one way of looking at it. You look at the formal education. This happens within the institutional framework. This is an organized, systematic approach, and it's carried out with a clear purpose in mind. To say it in a loose way is to be able to give a degree to a learner. There is also non-formal education. And this you can intuitively understand that this happens outside the institutional framework. Even this is often organized and is systematic. One example would be the kind of tuitions, that tutorials or tuitions people go to, or in the more recent context, it's the WhatsApp universities, or even ChatGPT for that matter. They're all components of non-formal education. They still have a structure, they're organized, but doesn't happen within an educational setup. The informal education is the one where daily experiences and exposures to the environment gives us knowledge. So in the context of this talk, I'm looking mostly at formal education. Okay, because often this question arises that why do people think that education happens only in the classroom? It happens in several fronts, but what we will be concentrating and I will be looking at is the formal education component. And this is a pedagogy is a word which we have been hearing a lot of now, but it's something not many physicists are aware of. It's something that physics people have generally not been very conversant with. Pedagogy, if you look at it, basically deals with an approach to teaching. It's a method and practice of teaching, incidentally. And it also involves theory and practice of learning with an emphasis on understanding how this process influences and is influenced by social, political, and psychological development of learners. So its pedagogy has to look at this additional component of learning, which is just not gaining information. The next thing is study of how knowledge and skills are imparted in an educational context and considers the interactions that takes place during learning. So what is very important is pedagogy understands that there is an interaction of the learner with the system and with the content part, and therefore the one teaching has to be slightly aware of these things. Pedagogy is something most of the B.Ed teachers in a very informal way learn quite strongly in their courses, but for some reason teachers and the system has always ruled that pedagogy is not of much relevance when it comes to higher learning, higher education. It appears to take a view that it's the content which is very relevant and no thought is generally given to pedagogy. In the context of the new education policy, national education policy, I think anybody who has left the draft of that have looked at this word very often. It repeatedly occurs in pedagogy. I am very happy because this is the first time anybody in higher learning, higher education is even talking of pedagogy. So let us see. I would like to today emphasize on what is this and what is its role. What do we mean by reaching a pedagogical objective while teaching. Okay, and as you can see by the three steps that are put up, pedagogy of theory and practice of pedagogy is very, very complex because it has too many influencing factors. I will today focus mostly on content pedagogy, which is a pedagogical skill teachers are trying to impart the specialized knowledge or content of their subject areas. So content pedagogy is specific to the content that we are looking at. So now, what are the pedagogical concerns? Very, very important is that the pedagogical concern is context specific. So therefore, I will concentrate mostly on undergraduate education in India. You can see that there are two components to it, undergraduate and India. The education system is very different in different countries. In India, we have a highly structured and a well-framed process of learning. Therefore, the education pedagogical concerns for us are very different from the pedagogical concerns in the West. And if you're looking at school or intermediate college learning, the concerns are different. Therefore, the context that I am going to concentrate today is for undergraduate education learners in India. It's very difficult to have a very global approach to it. Therefore, I would concentrate on this. And very important, then other important thing is that the pedagogical concerns are domain specific. So what do I mean by that? If I'm trying to teach music to somebody, or if I'm trying to learn some music, because I'm learning music, that's an example that comes to my mind very readily. So if I'm learning music, the kind of pedagogical concerns are very different from the kind of pedagogical concerns that would be there if I'm learning wrestling, for that matter, any sport. They're very different. So the pedagogical concerns, therefore, are going to be very domain specific. I will concentrate today on physics learning. What are the concerns for learning physics as a subject? So this is, I'm going to reduce my domain a bit, and we will mostly look at issues that are relevant to undergraduate education in India for physics learning. And where is the dichotomy here? The dichotomy is this. As students, some of my students are here today attending the talk, they would readily agree with me. Passing an exam and obtaining the relevant degree with good grades is the most fundamental objective of a learner. Okay. To do this, all you need is a teacher with a sound understanding of the subject, good communication skills, and students with fair amount of motivation, which is there most of the time. These are all given in a system. However, for the system or for the education scenario, what we want is somebody getting the relevant skill to learn and process domain-specific knowledge or domain-specific skills. You will see what I mean soon. Now you can see what the student wants and what the system wants are two different things. So I would put it as a cartoon here, and the student is sitting on a lot of information, and the only thing that interests the learner is to be able to understand and learn the subject, whereas the teacher wants them to do this. Get the entire domain specific understanding, the skill sets required for the domain specific learning. So therefore, there is obviously an impedance matching which doesn't exist. There is no impedance matching that happens. What are the requirements now to get the pedagogical objectives? The requirement is, first, most important thing is to understand how students learn. How do we even figure out how students learn? The currently available method is basically to be looking at their grades. And as teachers, you must have experienced this several times, that the marks that the student gets in an exam is not really very well aligned with an understanding of the subject or the difficulties that the students face. Therefore, the first thing that a physics education person would want to understand is how students learn. I understand that it's a very complicated subject by itself, but we can get a feel of what are the difficulties. The second thing is, what are the pedagogical concerns for physics learning? And the third one is, how do I realize these pedagogical concerns and how do I validate them? Okay, these are the three things that I will be required to look at. If you start by looking at the first part, which is how students learn, the first part is one has to be fairly aware of the learning theories that exist. I beforehand accept that I am not an expert in this area, but I have a fair sense of what is happening just by being exposed to these learning theories. And learning styles. How do students learn? There are different ways in which students learn. So I'll briefly outline this. I'm not going into detail to this. The learning theories are mostly, if anybody has some familiarity, it is behaviorism, cognitivism, constructivism, connectivism, humanism. These, and this list has no hierarchy. Let's be very clear about it. Or nor it, this is like the laws of thermodynamics or laws of mechanics. You don't have specific laws. This is a categorization which is generally accepted. I will not go into detail with all of this, but I'll just quietly say that behaviorism basically says that entire understanding happens as a stimulus to response relation. There is a stimulus and there is a corresponding response. That's the most fundamental theory of learning. And what is very interesting is that this has been a very, very old theory of learning. Cognitivism says that, yes, there is a stimulus. Yes, there is a response, but there are a lot of cognitive processes that happen at the intermediate stage. Basically, it's not just stimulus to response. And constructivism underlines that knowledge has to be constructed by the individual, not necessarily fed as a kind of a recipe to learners. Connectivism and humanism are a little more advanced theories. It's not very relevant for physics learning. And when it comes to learning styles, all of us are familiar with this. Some of us are visual learners, auditory learners. Some prefer reading and writing. Some prefer kinesthetic inputs. So when we are teaching a mixed class of students with different, I don't say potential, with different tendency to learn, one has to make a good combination of all of our approaches so that it appeals to most of the students, most of the learners. And there is also, I think, most of the people who are familiar with Bloom's taxonomy also know that another way of categorizing learning objectives, what is the objective of learning, comes from Bloom's taxonomy, where you go from knowledge all the way up to synthesis, and that has been revised again to make remember and go up to evaluation. This is something which, if one is interested, you can always pick up and read. Very interesting material. And there are many issues related to it. It would be going completely out of context to do that. I just want people to understand that there is a way of understanding how learning objectives are achieved. Okay, so then the next one is, now we will come to the crux of our talk, pedagogy in the context of physics learning. What are the concerns? Okay, first we have to identify what are the domain specific concerns. The second one is, how do I address them while teaching? The third one is, how to identify learning outcomes. These are the three things that I would be interested as a physics teacher. And this is where whatever we are talking of today comes in. Physics education research has given so much of input to understand the above concepts that we are almost ready to completely use the pedagogy of learning in a physics context. Fortunately, physics is way ahead of other subjects. I haven't really understood why. Maybe because there is a general perception that physics is a hard subject than others. Therefore, many people have been very, very keen on trying to see why physics is hard. There is a whole lot of literature available in this area of research. This has really evolved as a mature area of research where very good scientific principles and methodology have been established, mostly in the West. That's a slightly disappointing scenario. In India, where educational concerns are huge, for some reason, we haven't been able to catch on to this field of research. In fact, every physics department in the West, I was in Kansas State University for a year, every physics department in the Western country has a very, very sound physics education research group. And we hope that with IAPT really putting its foot forward, we will see similar development happening in our country also. I would love to see that before my time ends. Physics education research, as per what is put up on the Cornell University website, is the study of how people learn physics and how to improve the quality of physics education. It also says researchers use the tools and methods of science to answer questions about physics learning that require knowledge of physics. I'm quoting from Cornell University. Researchers focus on developing objective means of measuring the outcomes of educational interventions. So you can see that physics teaching or physics learning is simply not a process by which we obtain a degree, but it has objectives which are far above that. That's very important. And one of the objective to take physics education research is something what a student said. This is a learner of physics who said, to some extent, science is hard, simply because it is hard. That is to say, the material to be learned involves a great many concepts, some of which are very counterintuitive. This fact is well understood by teachers, the professor, and the general public. What is not as well understood are the various ways in which this already hard subject matter is even made harder and more frustrating by the pedagogy itself. So this is something which is very revealing coming from a research scholar from Cornell University, Eric, I think, if I remember the name. And this forms the reason why physics education research is a very, very worthwhile area of research to pursue. I would take a few minutes to say something of my own personal experience. When I was doing my master's, or even when I started doing my research in physics, when somebody asked me, what are you doing? I would say I'm doing my research, and then they would say, what subject? And I would say physics. And there used to be a huge appreciation which says that I am a very intelligent person. So they would say, oh, wow, you're doing physics. But then after a while, the same sentence, when it was followed by another sentence, that they would say that, wow, you must be very intelligent. And the next sentence would be, I hated physics. So it was something, even initially, it gave me a sense of pride, thinking that I'm doing something very worthwhile. But then when I became a teacher and started teaching, that sentence really started to hurt me. If majority of good learners, fairly intelligent people, have a feeling that they hate physics, where are we going wrong? The subject is very interesting to most of us. For the teachers, The subject is amazing. It's very, very intriguing. Whereas for many learners, they find it formidable. They have either dropped out of it, or the ones who continued are doing it very unwillingly. So it really then started bothering me that why is physics learning so hard? I didn't even realize there was a field of research which was called as physics education research when I started looking at it. Then comes I started figuring out what are the vagaries of this subject which make it so hard. Why is physics hard? Yes, it is simply hard because of several things that we talked of, but why is it hard even for very good students? The first thing, all of us agree, there are a whole lot of concepts that we use in physics. Okay, and these concepts have a language meaning and a physics meaning. So if I take a very simple example, which most of us are familiar with, I will look at the concept of force. In language, it has a context relevant meaning. You can say he was thrown backwards by the force of the explosion. She was forced into an early retirement. Force, the word force has a context relevant meaning. Whereas in physics, the force word has a context independent, non-negotiable meaning. You can look at the definition, but what is very important is that it has a non-negotiable meaning. I cannot interchange it with the force with energy or any of those, whereas in the language meaning, they can be replaced with some other equivalent synonym. That is one thing in physics that one needs to be very careful about, that its definition or its meaning is non-negotiable. And then comes more trouble. In addition to defining a concept verbally, we also have a mathematical definition of a concept. For example, if I say F is equal to M into A, where the letters represent physical variables, this again is new from what somebody has already experienced. Then the concept also has, as you learn more, quite a few concepts don't have a physicality associated with it. All the concepts which are related to concepts in mechanics have a physicality to it. You see speed, you see motion, you see force, you can sort of sense it. Whereas when you go to advanced topic, not all the concepts have a physicality associated with it. For example, electric field, electric flux, wave function, spin, there's no physicality associated with it. So this is an additional dimension which comes into effect only for physics learners. And further, quite a few of the concepts are not even tangible. Tangible would mean that you can sense it through sensory perceptions. So that also becomes an additional problem. And for example, if you go to the concept of wave function, it has no physicality, it's not tangible, but it's an excellent tool to learn quantum mechanics. Okay, so concepts have this problem. In fact, one of my students, Dr. Shubha, has extensively worked on some concepts. For example, she looked at how electric force is perceived by students, how electric field is perceived, electric flux is perceived. That was the question we started with. How do students understand concept which don't have a physicality associated with it? And they're not tangible components either. So I just want to show what kind of approach one takes up if you're doing this kind of research. So what we did was we generated questions which basically looks at electric force, electric field, and electric flux. These are the kind of questions that we give. We give it to, these were the undergraduate students who were doing this kind of a test. And this was a question on force. I will not go into detail about the questions. If anybody is interested, please get back to me. Shubha and I will be able to give you further details. For electric field, we had a question like this. You had 2 point charges that are arranged, and we said, what is the electric field at this point? And the responses of this question was something like this. You can see the B component, which is the correct option, was picked only by about 15% of the students. Okay, so when you design the question, you have to be very clear about what are you looking at. We wanted to see, do students know how to represent electric field vectors given a charge distribution, a charge setup. We took a dipole charge and then we asked them to look at it. They have to use electric field definition and also principle of superposition to get this. This was the response. So this is the kind of questions that you ask. And there is the other example that I'm showing you. That way you have to probe further. When you look at the responses, you don't get any deep understanding of what the student is thinking. Therefore, you generate questions which will look at the intermediate stages. And these are the kind of questions. See, these are some of the incorrect representations that the students come up with. And you can see that there is a, this is a few of them which I picked up. You can see that there is a major confusion about how to draw the vector and how to even get into the idea of concept of electric field vector. So what is important is to see where the difficulty lies. What we did was to look at the concept, outline of the methodology is something where we gave them a simulation exercise and the concept of electric field, and then tried to see how they worked on it. So the details of this I can give you if anybody is keen. And then this is not the end point in physics learning. You begin with understanding concepts, and I have shown you that there are a lot of difficulties in understanding physics concepts, whereas it doesn't stop there. With physics concept, you also have to progress and then look at processes. Physics is just not about learning concepts. One has to also learn processes with it. And some processes are tangible. So when force is applied, object accelerates. That's a tangible process. And what do you do when you try to understand that? You will end up looking at displacement and time relation of the process. So this is a fairly easy process. Suppose I look at another process, which is not tangible. Look at electrical conduction in metal. Okay, my final purpose is to understand electrical conduction, but I really cannot visualize what is happening inside a metal. Therefore, I model the process in a qualitative way. All of you are familiar with the Drude's free electron theory. It starts with that. You treat the electrons as gas molecules, neglecting the interaction between the electrons, and then you use kinetic theory of gases, and all new concepts like drift velocity, all of those come into picture. So we initially start off by modeling the process in a qualitative way. Okay, and what is the purpose? I want to find what is the relation between electrical conductivity and some relevant parameters. It depends on the process. So this process is an example where the process is not tangible, is not visualizable through sensory perceptions. So when you are learning physics, an important paradigm shift happens when we go from qualitative description to quantitative relationship. Otherwise, the story of physics that I'm trying to say has to stop at some point. It doesn't give me a validation basis. Therefore, what we use when we do physics is we use mathematics as a useful language. This is another hurdle for many students, especially in the undergraduate scenario. They perceive the mathematics used in physics as a big obstacle for understanding. I think one thing that needs to be done at this stage of teaching is that this quantitative statements that we make, not mere qualitative statements, the quantitative statements, if we can show them that how much additional information comes from it because of using mathematics as a language, I think it's a big step. So there is no way that you can avoid mathematics, and there is no need to avoid And especially if you can really see the beauty that the mathematics brings into physics. So therefore, the additional step of difficulty comes because mathematics is used as a language. And because mathematics is used as a language, we use symbols to represent physical variables. I don't write force as F-O-R-C-E. I just represent it as force. We use symbols. And therefore, at the end of it, we want to find what is the relationship between the variables. When I derive something, that's all I'm trying to state. I'm trying to see what is the relationship between the variables. Okay, so now math in physics is very different from math in math. For example, if you look at a math equation, Z is equal to X into Y. Nobody, not mathematicians, not physicists, not even biologists have any objection to this. But suppose I write an equation like this, A is equal to U into T. All of you will practically kill me for doing this. Why? The physical variables A, U, and T actually are physical variables. The physical symbols are variables. A general tendency is to use A as acceleration, U as velocity and time. And by the definition of these quantities, you know that this equation is an absolute nonsense. It doesn't even make any sense. And after that, you have something called as a decorated physics equation. I call it as a decorated physics equation. You are adding attributes to variables now. And I say V is equal to A into T, where the arrow, the semiotic representation that I have shown here, tells me that it's not just a physical variable. It has an additional property that in addition to magnitude, it also indicates a direction at a very, very basic level. So what is the consequence? Equation in physics is a relationship between variables, with variables being represented by letter-like symbols. And you have seen that how many alphabets are there in English? Even if you take the small and the capital, go to Greek, go to Italian, all of those, there are fewer number of alphabets and innumerable number of physics concepts. There is a huge degeneracy because of this. So it is inevitable that for the same, for different physical variables, I have to use the same physics symbol. For example, H. If I say H, depending on the context, it can be the height or it can be the famous Planck's constant. So therefore, the degeneracy in the symbol is something which is very, very difficult for students. Whatever has been learned at an initial stage, that sticks in their mind. I will just quickly give you one experience that as a teacher that I have felt. I think these experiences are the ones which make us into PER researchers. I was teaching them about Coriolis force, and I was deriving an expression for that eastward deflection of an object when dropped from a certain height. If you recall, it's a fairly complicated derivation, and they actually find what is the eastward displacement in which H is used as a symbol, height is used as a symbol H, and you get a relation in terms of height from which the object is dropped. And in the test, I told the students that it was a test for 10 marks. I told the students I will give them 1 mark for derivation and 9 marks if they can identify the symbols at the end of the derivation. Just identify them. About 80% of the students made mistake there. Which means to say that if they can remember and recall such complicated derivations, there is no way that they have difficulty associating the variables with the symbol. So while teaching, one very, very relevant pedagogical objective is to ensure that they realize these symbols represent physical variables. And at the end of doing some derivation, if you can ask them to state it as a physical relation between variables, I think after that cheating test that I gave, nobody did that mistake. It had become a habit for them that they would always identify the physical variables and the letter-like symbol. So that's that degeneracy. In fact, our own research, Hegde's work, on problem solving has clearly shown that one of the reasons why students have difficulty in recalling the relevant physics principles is this degeneracy, that the symbol that is used for physics as a physics variable gets very confusing for them. Okay, and there is also the mathematics, because mathematics is a language, the mathematical tools, I just need to be aware of where I am. Yeah, the mathematical tools that we use are also very, very strange and difficult for students. The mathematical objects that we use are functions at the basic level. Then we use slightly more strange vectors, differential operators, integrals, whole lot of them. And when we use this mathematical tool, there are two things one need to learn: the mathematics of it. You need to get a conceptual understanding and also the procedural knowledge. How do you use these tools? The rules that are there for using them. The next level of complication, therefore, comes: how do students learn the usage of mathematical object? The second one is to know the associated procedural knowledge, and in addition, use it in the context of physics. Okay, so using mathematical tools has this additional requirement. Therefore, at the end of doing all of this, when they have learned vectors, they should be able to see that this particular statement, vector A, vector B, or vector A dot B crossed with C, they're all senseless statements. For somebody who don't know vectors, it's fine. But otherwise, for a physics student, they have to feel very uncomfortable when they look at these things. That's the objective. And also to be able to see the difference between dou psi by dou x multiplied by the psi star. We do this in quantum mechanics all the time, or the next statement. Those two are very different, and which you can get it across by taking one counter example. That's sufficient. And to be able to see that when you have a term like this, the numerator here has to have dimensions of energy. Or if you recall what you do in statistical mechanics, you use the argument of dimensionality to define this d by de of ln omega as the beta 1 over kt quantity, or the argument of a sine function has to be dimensionless. So these are the subtle things which come by knowing the procedural rule, procedural knowledge of those tools. So these are fine aspects that they need to learn. And my student Usha has done extensive work on understanding this vector as a mathematical object. And we all know that in introductory physics, mechanics, electrostatics, magnetostatics, electrodynamics, we use vector mathematical tool extensively. And that's also because it gives additional information in addition to magnitude. Vector properties and its operations have to be learned very specifically. Vector algebra and vector calculus need to be learned if you are using vector as a mathematical object. The more complicated thing in the context of vectors is this: vectors have several different semiotic representations. Semiotic would mean symbol-like representation. If I say plus, it means addition, right? So that kind of semiotic representation. And each representation comes with its own attribute. They have its own properties. I will give the example. And understanding or interpreting each representation and to be able to switch between representations becomes extremely important to understand physics or to be able to express that. So this figure basically tells that in mathematics, you use vector as a mathematical object. And the representational formats are these. You can express a vector as a verbal, in a verbal statement. You can represent it as an arrow. You can put this as an arrow on the grid, or you can have a graphical representation with the XY coordinate axis in the Cartesian system, or you can write it as a component as an AX comma AY, or as an IJK unit vector. I have shown a two-dimensional vector here, but there could be the third component also, third dimension also. So now you can see the same object vector has different representations, and none of these representation is complete by itself. They complement each other. For a physicist or for somebody who uses physics for their livelihood, These representations are very well understood. And in a given context, you know which representation gives you more information. And also one knows how do you go from one representation to the other representation. Whereas for students, we wanted to see how difficult is this mathematical object. We used what is called as test for understanding vectors. This is popularly called as TUV by Barniol and Zavala. This is considered as a standardized test for trying to probe how students understand vector concept. It's available online anywhere, it's for free. So what we did was, it basically is a 17-item multiple choice question test. We inducted this for about 250 students, I think. If Usha is there, she can correct me. About 250 students. And we did an extensive analysis of the responses. And we developed our own questions to validate our analysis. This was the method that we used. Though we used test for understanding vectors, which is a readily available standardization test, we also developed our own questions to do it. I have just shown you 2 samples of the questions. If you can see the question 1 here, basically is looking at the addition of 2 vectors when the vector is represented as an arrow on the grid. Okay, you can see vector A and vector B here, and the student is to pick the answer. And you can see that in the question has an arrow on grid representation. The option also is arrow on grid. Whereas question number 8 has 2 vectors in the algebraic form, and they are to calculate the dot product of the 2 vectors. Okay, and this is the kind of question. All other 13 questions are extremely interesting. In fact, last year my project students were trying to get some additional data on TUV. In fact, the teachers who gave TUV got terribly excited about it, and they were sitting and doing these questions. It's very, very interesting to do it. So we collected it from, 250 is right. And we also used classical test theory to calculate quantities like difficulty index, all of that, the details of which can be gotten from many verses. And then we also, very interestingly, this is additional to what was done before, we looked at each question and categorized the question based on the representations used. We said that what is the representation used in the question statement? What is the representation used in the option statement? So we did a detailed analysis of that, and the results they're too exhaustive to discuss completely here. It clearly shows the representation has a strong influence on understanding. And arrow representation was much harder than the equation-based representation. So this sort of gives us an insight into what we take it for granted. When we are teaching, I don't think we look into that fine aspect of what are the difficulties that the students face. Okay, so because these difficulties come not because of bad teaching, it doesn't come because of a bad learner, it comes because physics as a subject has these inherent vagaries. So one has to accept that and see how best one makes use of it. And then the other object, mathematical object that she looked at is also mathematical functions. Okay, so how do you understand functions and how do you understand its representation? This is something my students, if they're here, they will know. I'm a big fan of Desmos. I don't know how many of you have, it is a freely available app where you can plot functions. I mean, it's an amazingly user-friendly tool and very insightful both for teacher and for learner. So whenever I say something, I write an equation, I tell the students, plot this in Desmos and see how it looks. So this is just as an information. So what the concept that she was looking at was maxima and minima of functions. So this is the mathematical tool that we were looking at. So this is the flowchart of her work. This is literature survey design of questions and okay. We picked up mathematical problems on functions and we used Desmos for online graphing. And we took another set of problems, physics problems, where the concept of equilibrium is relevant. And that comes in many topics. Therefore, we took those problems. I think we took the Gibbs free energy problem, and I think a nuclear energy minimization problem, 2-3 problems where it was important for students to calculate what is the minima or maxima of a function. So this again, we did an extensive scrutiny of responses, and then we did the scaffolding interviews, teaching learning interviews. So it was an exhaustive work. At the end of it, we understand that function and maxima and minima is not a very simple thing. It was slightly easier in the mathematical context, but in the physics, it was much harder. I don't have the time to really completely tell you the details of it. Again, you are welcome to ask for any clarification from me or Usha when it comes to this. Another thing that I'm only making life more and more difficult is due to the multiple representations that we use in physics. For example, we use verbal representation, pictorial representation, and we also use graphical. Okay, so for verbal representation, very important is the language cognition. And in our country, we being a multilingual system, English has been a weak spot for us, for most of us. In fact, if I remember, one of the clear suggestions of NEP is to be attempting to teach language content in our own, I don't want to call it as mother tongue, is local language. My personal views on that doesn't really matter. But what is very important is that language cognition, lack of language cognition interferes strongly in understanding the expression, understanding and expression. Now, this is my own expression. My students won't like it. Suppose in an exam, if there are 3 questions of this kind, just say that prove d rho by dt is equal to 0, state and prove Lyell theorem, and the explicit statement of the Lyell theorem. I have often seen that the question, if it is in the form, in the last form, which is a verbal statement, has very few fan following, very few people in an attempt it. Okay, and even in the TUV, test for understanding vector, there is one question which has an explicit statement of orthogonality of vectors. And that question had the least correct response from students. So language cognition and to be able to do the mathematical derivation, I don't know, all of you must have experienced it. They start very beautifully, go for pages together, but you don't find any connecting English sentences in that. So, which means that it's not that they don't want to do it, but it is a harder thing. So language, strengthening the language ability is very important, and there's no shame in it. In fact, I tell all my students, there's no shame in saying that you can't really speak English well, but it interferes in your learning. So it's worthwhile to put some energy into learning. If you can learn physics, learning language is not going to be difficult at all. Okay, so the next thing that pictorial representations we are all very familiar with. Generally, it is used to supplement information in the statement, in a problem statement or a physics context. It complements sometimes the statement, but when you are dealing with situations where the concept or the process is abstract, we have problem in pictorial representation. So you can't really draw pictures when you're doing a quantum mechanics problem, or you can probably understand the results, the psi star kind of a behavior, but not really write the statement of the problem using pictorial representation. Graphical representation is extensively used in physics, and Dr. Usha again has done work on this. Basically, it is a process where one represents the relationship between variables pictorially. All of us are very comfortable with this. And research has shown, and even Usha's results have very clearly shown, there's a difference in the way teachers and students perceive graphs. I use the word expert versus novices as a content expert and a content novice. There's nothing derogatory about calling it as expert or novice. Students who are learning how to use these graphs and teachers who are using this as a graph. We have done it with teachers also. Give 2 to 3 different paragraphs, one which has a pictorial representation, the other verbal representation, and a graph. A trained physicist quickly looks at a graph. A graph tells you much more than what those sentences say. So therefore, graphical representation is used to an advantage by teachers, whereas learners find it formidable. Okay, so which means that you cannot take efficiency to use graphs for granted. Okay, so Usha's work again is this has the same flow chart. We looked at math problems and we talked of slope and area under the curve. Sanjay Rebello has done extensive work on area under the curve and the integration as one of the graphical efficacy. We took physics problems. We looked at graphing, linearization, analysis, area, and she has identified the skill sets required to enhance graphicacy. This is there in a paper also. She'll be able to give. So this basically tells the identification of different facets of graphicacy that is necessary for physics learning. So now we have seen what are all the difficult things about learning physics. Now, what are the implications for teaching? My personal belief is this. I would like to emphasize on this a little more. So for a teacher, we are not teaching mechanics, electrostatics, quantum mechanics, statistical mechanics. No. I am not looking at me teaching versus Mr. or Mrs. X teaching. That's not the concern at all. The concern is to be able to impart the skills required for robust understanding. So it's the skill set that we are teaching. When I'm saying I'm a physics teacher, I'm only teaching the skill sets required for learning. I strongly personally believe that the content that we teach, it could be anything, it could be mechanics, statistical mechanics, anything. The content we teach is only a vehicle for teaching these skills. Okay, so when I'm teaching, if you have a general feel of what are the pedagogical difficulties learners have, emphasize on those learning skills rather than on the content. I remember once 2 of us were teaching a classical mechanics paper, and I asked the student to tell me what is the Lagrangian of a, I think it's a pendulum, a simple pendulum. And they asked me if I was asking for Meera Madam's Lagrangian or Care Madam's Lagrangian. So it's the concept becomes so strongly embedded with the teacher that they realize, they forget that it's the skills that they are learning, and we forget it's the skills that we are teaching. Our teaching mostly gets completely overwhelmingly complicated because we are focusing mostly on content, not on the skill sets. So remember, content is only a vehicle. You cannot teach the content without any context. You cannot teach graphical efficacy or vectors without having some content as a basis. Therefore, I implore all of us to remember that what we are teaching them is the skills required for understanding, and the content that I'm teaching is only a vehicle used for teaching those skills. And I'll spend a few minutes on, because this is something which many people ask. I think I have 5-10 minutes, Sapna.
Yes, ma'am, you can take 5 minutes. Yeah.
Okay. So the next step is having understood the pedagogical difficulties, I want to say a little about how do you validate these objectives? How do you do them? So the most important thing to understand is we have to realize what questions to ask is very, very pertinent in the entire scenario. We are not interested in seeing sort of marking them as the right answer or the wrong answer. That is not our purpose. We want to see why a particular answer is something that the student says. So the algorithm that most of us are familiar, Professor Chetralekha also talked about it. There is the first requirement is to be able to understand the student initial state. What is their initial understanding? We have to understand learning happens in a very complicated manner. It also happens in an informal setting, formal setting, non-formal setting. Therefore, a student who comes to class has a earlier established initial state. Okay, so how do you probe that? You have to give a pre-test. And then you use a teaching with a clear pedagogical objective, looking at the course outcomes, and then you evaluate using a post-test. I do agree that it's not very easy to do it in the Indian context. In the West, a given class or a given course is completely tailored by the teacher. I have attended a course given by Sanjay, which was only reading papers from journals. Okay, and there was no examination. We were completely evaluated based on our analysis of those papers. So that kind of freedom is not available in India, but there's a lot one can do within our confines. We have been able to give pre-test. We have looked at pedagogical objective. We have evaluated post. It's possible, but you can't separate them in the given class itself, but you have to do it in addition to it. So it's possible. Question design becomes very important. So the procedure is generally to design these questions. You start with an open-ended question. In the open-ended question, you give it to some students. The larger the numbers, better is your input. You analyze the responses. So which means to say that with each response, there will be some muddled answer that you see, but we should be able to identify why that particular answer is coming in their working, and use these responses to design the MCQ options, multiple choice question options. Then this multiple choice question options will have to be given for a validation. We call it as a validation test. So you give it to a smaller number of people just to ensure that the question is basically doing what you want it to do. Okay, that validation test is important. Then you collect the sample data, and larger the better. And in the Indian context, it's a very, very easy thing to do because we have large number of students. So it's and then you use do the data collection, you analyze the data. There can be two ways of doing it. One is collect large sample data to make valid statistical analysis. If you want to do a statistical analysis, the sample size has to be significantly big. Otherwise, if I have 10 students and I collect the data for 10 students, it really doesn't validate the statistical procedure. Or you can, if you have a smaller sample, you take the data and use this MCQ format to design teaching interviews. We design the teaching interviews using these responses. Then you transcribe and analyze. I will just say, illustrated this in Hegde's work. My student worked on the difficulty students have in problem solving. We took a problem of this kind. And this is the pilot test response. This is the correct response, the one in green. So we have designed a protocol, interview protocol, which has been highly appreciated. Our physics education research special review topics, that has a paper in that. I think this is the second paper from India, which has come in this journal, where we have defined, generated a scaffolding protocol. This is the interview protocol. We say that give the question. If you have incorrect answer, we go through this procedure. If you have the correct answer, you go through these branches. This is the mind map of the question. So we have generated this kind of question. How did we do that? We used our MCQ responses to generate this mind map. We took the response from students. Those responses were used to generate this. You get a feel of what the student has a difficulty with. Okay, and this we did it for all the 8 problems that we investigated. And this was given for teaching interview. So this became the basis on which we do this teaching interview. So you go through the exactly identical steps for every interviewer. So that's the learning outcome. Okay, so yeah, this is for the earlier one. And the objective is basically we were trying to see how problem solving gets more and more complicated by inefficient understanding. So it was in that context that we were doing this. And what is very important is that to understand the learning outcome due to the pedagogical initiatives, the questions that we ask must align with the pedagogical approach. The question one asks become extremely important. So if you see the question designs, that itself is a research activity. The kind of questions that one asks have to have a clear idea what we are looking at. And you have to test those questions with a sample size and then continue with the data analysis. And another difficulty which students have is also to integrate class and laboratory learning. I was a part of the studio physics laboratory of Dean Zollman for the 1 year that I was there. And we are trying to see if eliminating the boundary between lecture and laboratory. I can't talk much about it right now because I haven't analyzed our results on this initiative. But I have a qualitative understanding that this approach really helps students to
Madam,
learn.
we have to wind up.
Yeah. This is the last slide.
Yes.
Okay. So we have to eliminate the boundary between lecture and laboratory. So I have designed what is called as a studio laboratory, where we tightly control what is taught in class and what is done in laboratory. Exactly what is taught in class is what is done in the laboratory. So the studio physics lab, we are yet to do the analysis of our results, but this is one initiative that seems to have really been very useful for laboratory learning. So all I'm trying to say is physics education research has so many components and so many facets. It's really hard to do everything in one talk. I tried to focus on the ones which our research group has focused on. So the details of which you can always get back to me if you really need. And that's what I wanted to say about it. I'm sorry if I overshot. Yeah, okay. Thank you.
Thank you so much. Thank you so much. You are very much in time. Any questions, please? Hello, any questions? Am I audible?
Yes. Yes, sir. Audible. Yes, sir. I have a doubt, sir. Namaste, ma'am.
Namaste.
I'm Sesh Kumar.
Yes,
from last 15 years, I'm working in a degree college.
Okay.
2-3 years in between that one, I'm working in a PUC college, intermediate college.
Okay.
I'm clear that CSIR net and PhD and this AP set and GATE, everything exams cleared, but I don't have that BD examination. So I don't know this technical word, the pedagogy, that word side, I'm not understanding clearly, but your approach is very excellent. And what is exactly what I'm facing the problem here? Where I'm working in degree colleges, so many schools, they are going to approaching to me. And even the degree students, where I was observing that one, they are not up to the standard in science education, particularly in my physics. So I have to start to solve this problem from students itself, from students levels, that particularly from high school level onwards. So I want to approach them at least weekly or monthly. I want to visit a school, at least on Sunday or working days, and I have to prepare some online videos also.
Okay.
Particularly what you are going to say, that the last word with the demonstration. That means the class teaching must be happens only in the laboratory with the demonstration. Then only I think the students are going to understand more clearly the concept. And the way what you are going to explain that one, how to analysis the students' result. That means outcome results. That means how to prepare the questions and how to analyze that one, how much extent they are going to understand that one, and how their application skills are there. These things I want to learn that one from you.
Yeah.
Actually,
I am there for anybody and everybody, sir. That there is no problem with that. But what is very important is, like you said yourself, the kind of question that we ask is the most important aspect of the whole research area.
Yes. And
because
one thing,
I have tried it with our students. I mean, just give me a second. If you ask the students, why do you think so? I have tried this.
Yes.
They give a response. I have asked them, why do you think so? And they're tight-lipped. I've never come across a student who can put their thoughts into words. So which means the intermediate questions that you ask has to unfold their thought process. So that question design is the most critical part of PER. Yeah, that's very nice. Yeah. I'm sorry, Madhurima. Doctor, sorry.
Sorry.
It was a really nice talk, undoubtedly. And you have actually covered most of the important points. I have 2 comments and 1 question. Okay. The 2 comments, one was about reuse of symbols, and the second was about physicality of parameters, the word physicality that you used. The comment I had about reuse of symbols is that one way to overcome it, or at least what my teachers taught us, is they gave us the freedom to use any symbol that we want. We were not constrained by the symbol. So I could define at the beginning of my answer sheet that, X is Planck's constant. And so if I was consistent within that answer, they would accept it because they were willing to spend that effort. On the other hand, I've had very miserable teachers, and this actually happened to me in my undergrad, where because the record had to be neat, I wrote, instead of half I omega square, I wrote 0.5 I omega square, and my teacher called me and said, this is a wrong formula. I'm like, how is it wrong? And we had a huge debate. So you get the idea. So the other comment is about physicality of parameters. The only thing I feel is those parameters have physicality. It's just that they don't have physicality within the human experience domain.
Yes, I said physicality only with respect to sensory perceptions.
So I think that quantifier to that is required because
it has an ontological attribute. It has an excellent ontological attribute.
That bit of a difference needs to be brought out because they do have physicality. The question that I have is more of a pedagogical question, which is, you have been using the word pedagogy. I know this is what is used, but is that not the problem when it comes to HEI, to higher education? That we still treat it as pedagogy, use the tools of pedagogy and not andragogy. We are not willing to treat our students as adult learners. True. Whatever is still, where do we allow them to start defining their own ideas, expressing themselves? So you get the question, I'm sure.
Yes, absolutely. Dr. Madhurima, this is something which is very different from the West. The fact that you said we don't treat our learners as adults and capable of making decisions, making mistakes, and we are so caught up on being right all the time, I think that takes away freedom of thought for a lot of people. That's one thing. And the other one with respect to symbol is something we all laugh about. My colleague Usha must be around for the talk. She sometimes, when she's using notations, she used to say, okay, you don't have to use X, Y, Z, call it Meera madam, call it Usha madam, call it Sharvari madam, it doesn't really matter. But I have tried that. Sometimes 2 people share a paper and the notations are different. And I find that the students get terribly confused because of that. It's only because we haven't told them it's only a representation of a symbol. It has no other meaning beyond that. So I think we have to first train them, loosen them, the rigidity of using the specific symbol for everything. But then there is also a universality that is required for content management. So I think sticking to symbol is not a very bad idea, but with a clear suggestion that even if I change something, nothing about the physics is going to change.
Again, a great talk.
Thank you.
Yeah.
Hello,
Professor
Dr. Meera.
Ahluwalia wants to.
I'm sorry.
Professor Ahluwalia has also raised his hand.
I'm sorry. Yes, Professor Ahluwalia. I'm.
Sir, you are muted.
Yes, sir.
So, Ma'am Meera, it was a wonderful talk. I have no words to express
No, I have squeezed too many things, but I couldn't help. I'm sorry.
for what you have done to this series. I think you have set further the tone of this series itself. And I think that is the best thing which has happened because of the itself. The sweep
you.
was so much that you covered very many things which can be, initiated. Anybody who wants to do physics education. I think that is another point which I really take. I think, ever since we started talking about this physics education research series, we have a few other also things in mind, which are very closely related with what you have discussed in this lecture. One is that there are some very interesting, say, as you talked about TUV, there are other inventories also which needs to be tested in the Indian context.
Absolutely, absolutely.
No work has been done in the Indian context for those inventories. For example, FCI is one for which I don't see any visible, context anywhere where we talk about or compare what has its influence in India compared to what was happening or what is happening in West.
We may have to tweak the questions a bit for FCI because their context is slightly unfamiliar for Indian. I think Singh Homi Bhabha Center has tweaked some of the questions for FCI for Indian context.
Actually, what we have been trying at the level of IAPT is we are requesting people to translate these concept inventories into
A local language. Okay.
Language.
Yeah.
In Hindi, it has been there. Professor Pradipto is sitting in this lecture. Also translated that into Bangla. Work has also been done for Punjabi. And we are requesting many other people also to do that for FCI. And I think a similar thing can be done for TUV also. That will be a very interesting part about all these things. There is another very interesting aspect which you kept on referring this time, and that is very, very relevant. And that was in the context of national education policy. Because, it has many implementation problems, no doubt about that. But it has raised some very, very relevant questions.
Absolutely. My call is only that.
Yeah. So, and it also brings us to a situation where whatever may be, the content which people may propose in their different universities, IAPT has a duty that we should really create a content which we deem is relevant with all those course objectives or the learning objectives or the learning outcomes which we talk about and presented to the people. This is how this needs to be looked at. These are some tasks which we need to look at, and holding this series of lectures basically is to underline these needs. That is what is our aim. And also to highlight, the Indian scientists who are doing work in this field, because many a times we do not know who is doing this work. Maybe we appreciate. I was seeing that your work has been noticed of that PER physical review issue by a large number of people.
Yeah, it has very good citations also.
Yeah, more than I think
150, I think now.
Yeah,
close to
more than 200 citations.
Last I saw, okay, I haven't kept track.
So I think that needs to be brought to the notice of the physics teachers so that they start feeling the reason why they should work in these areas also, which are being discouraged. And I and you both have seen that it was even very difficult to face the degree committees when we were going to present all.
You know that.
Fortunately, now that inertia is going away, that barrier is going away. Professor Shastri has been, doing wonderful things in Dharamshala to really initiate this as a very interesting part of the physics department. I think that is
Yeah. Yeah.
that we have been able to do that.
Yeah.
There is another need which I feel we need to really look at, that this series of lectures need to be brought out as a set of proceedings or book.
Okay.
And that is also I am looking at, because if we can have this, and if we can do it at the level of maybe an e-book, if we do not have money, e-book is also very, very relevant.
Yeah.
So if we can have, say, 12 or 15 such lectures together, as was done, I think, in the case of Physics News, ma'am, you must be remembering.
Yeah.
There was a book which was brought out. And that was really a very good initiative.
Yeah.
We need to have that kind of initiative also. And I
Anything that you want me to do, Professor Avale, I'm there. I'll retire in 2 years, so I have all the time on earth.
Yes. So I would like that you please lead that kind of initiative.
Anything that you want me to do.
Very hard.
Yeah.
We had wonderful lectures from Chandralekha Singh. You were there in that lecture.
Yes.
Earlier, there was one lecture by Mashood, Dr. Mashood.
Yeah.
From
I was traveling then.
So I think I don't have any words to express my sincere thanks to you. There are many questions.
I could only give a flare.
One more hand is raised.
Yeah.
Professor
Dr.
Jali
Jali
wants to ask question. Yeah.
Professor Jali.
Hello, Meera.
Hi. He's my friend from.
Yeah, very nice presentation.
Thank
you made a mention that physics is very hard. The barrier of physics, it is the communication language. It is English, because the student has difficulty in grasping English. He cannot communicate nor he can grasp. So in English, what is our effort? Even take example of Kannada. How much physics we have to put in our own mother tongue.
Yeah. Dr. Jali, I have a slightly different view on this. See, learning language really is not very difficult. It's just a practice of expression and comprehension.
Student has difficulty in understanding language because that he is unable to grasp physics.
True.
Physics
so if
no
they learn,
language.
if they put in initial effort to learn language a little more, because see, in English there is so much of resource that's available to them, whereas in Kannada or the local language, they get very constrained. There's very few little. See, I mean, you have looked at a beautiful Reef statistical mechanics book, right? Every sentence in that is a delight. So I just don't want these people who don't want to learn things in English to lose out on that. That's all. Other than that, I mean, the NEP, in fact, propagates heavily on teaching in the local language. But I don't see a solution.
I'm only commenting. We do not have any developments in our local language as far as physics development is concerned.
True.
Yeah.
We have, especially science subjects, as you say.
Yeah.
I think we have
because of that it has become hard.
True, absolutely true. In addition to it, there are so many hardships that I sort of mentioned, but language cognition is a major problem. You have seen that cause and effect gets completely interchanged. Zeeman effect causes magnetic field. I have read this sentence. So cause and effects get completely confused.
Okay,
you have been a teacher for 30 years now, right? So he's in Gulbarga University. He's a professor there, a very senior professor. So very keen on education.
Same as yours, not senior.
Okay.
We are retiring together.
Yes, we both are. Yeah.
So
thank you so much.
Yeah.
Thank you. Sorry.
I'm not seeing any question in the chat box. And,
there was one on 1 second on curriculum. Yeah. 1 second, let me. I think I saw. Yeah. Somebody, can I read out? I think it's a relevant question. Just a minute. In school education, it's common to encounter certain physics terms that have not been previously mentioned in the syllabus. However, these terms are introduced and discussed within specific topics or lessons to broaden students' understanding of the subject. I completely agree. There is no chronological order in which things happen in physics. sometimes I have seen that students learn velocity and acceleration even before they have a sound understanding of vectors. So wherever possible, we need to correct them. I think even when we go for syllabus revisions, we always try and see if there is a chronological order of doing things. Recently, my nephew asked me a question about cesium clock. It was so hard to explain to him. There is degeneracy of the energy level concept. There is superfine interaction, which will cause this degeneracy lifting. How do you even teach a 11th standard student about these concepts? So then they become mere words. So one has to be a little careful when we design the curriculum. Absolutely, I agree with you that we end up telling students things that they have never learned before, and it sort of makes them lose faith in the process. I hope the teacher has to put some extra effort to push in some more concepts, ideas. I think that's the, yeah.
That's the last question. That was the last question. We don't have.
And somebody said initiative, my email ID is here. Anybody can reach for me for anything.
Yes, thank you.
Yeah, it's a group of, it's the initiation of very dedicated teachers of physics, which make this thing happen. So there is no dearth of good teachers in our system. So let's take it forward.
Yeah.
Thank you, Sapna.
Thank you. Thank you, Meera.
Thank you, Professor Avlia. Thank you. Thank you.
Yes. Sastri ji is there? Sastri
Yes,
ji?
yes, ma'am.
Yeah.
Thank you so much. It was a very, very, very wonderful session. We really enjoyed it. And even though I was in the mall, I was not missing even one sentence. Every part of every slide I have gone by zooming into my screen as well. Madam, as usual, has done a very, very systematic and thorough job. Thank you, madam, for your efforts to promote this extremely difficult, discipline.
Very satisfying.
Yeah, I know. So at the end of 25 years, you can say that I have taken a bold decision and lived up to it.
Yes, yes, sir. Yes.
I hope that we also will be able to do. I hope that we also will be able to do the same. So now I would say, Shanti, if everything is fine, then we will end with a prayer for world peace.
Right. So thank you.
Samastaloka Sukhino Bhavantu. Samastaloka Sukhino Bhavantu. Samastaloka Sukhino Bhavantu. Om Shanti Shanti Shanti. Thank you.
Just one announcement I wanted to make.
So,
may I would request the participants of this workshop that if they have knowledge of any physics education researcher who can participate in this kind of series which is there, we would welcome. I think as Ma'am Meera has been mentioning a lot about two people. One is Usha Rani ji, she was there in this lecture also.
Yeah.
Other is Professor Hegde. I think we would love to connect with them, and if we can really make them part of this series, that will be very nice for us. Plus, there are some members in this group who are not the members of IAPT. I would request that they become members of IAPT. You can visit our website www.indapt.org.in. And I think I will write it down here in the chat box also. Please go there, explore our website. More such things which will happen. I think more will be the dialogue which will be happening in the community itself. So I would request you that. Thank you very much.
Thank you.
Thank you very much. Thank you very much, Meera ma'am. It was a wonderful session. Wonderful session. Yeah. Thank you very much.
We'll meet.
Yeah, definitely we are going to meet again.
Hello, Dr. Sridhar. My classmates from MS here also.
Oh, great.
and my colleague Usha.
Mm.
It's so nice, but I see her every day. It's okay. My